The form we've looked at for complex numbers so far is the Cartesian type form, sometimes called rectangular form, and that's z equals a plus bi. Now we also need to be able to work with complex numbers in something called polar form, okay? And polar form is also called the modulus argument form. Now modulus argument form means that it has two parts that are important. The first part, the modulus, you've seen before, and I've just got some notes here on the modulus. Remember, the modulus is the distance from the origin, okay? And if you're talking about a situation like this with an angle, with a complex number, which we'd call z up here, and z, if we were to create a triangle based on where that z is, a across and b up, okay, then we'd have, using Pythagoras, a squared plus b squared equals the length of this part squared, which we're going to call mod z. So it would be mod z squared equals a squared plus b squared, which implies that mod z equals the square root of a squared plus b squared, or the square root of the imaginary and real parts squared, so the real part of z squared and the imaginary part of z squared. So we've seen that in a previous video, how to find the modulus. Now in this section here, we're actually going to be referring to the modulus as another letter rather than mod z. We're going to be calling it r, okay, as we progress. So you'll get used to this idea that the modulus of z can be represented as mod z, and it can also be represented as r, okay. Now we're going to be looking at the next thing here in the polar form, which is called the argument. Now the argument is quite simply the angle, okay, and so in your books, in your notes, you definitely want to write down this title here and write down the diagram here of a typical complex number, z equals a plus bi, and you can see we've got 2 points here, the origin O and P, which is just a point in space. So we can also talk about this as being a line going from O to P. So if you see this notation here, that's just the line that's going from O to P. It's a vector. We haven't looked at vectors yet, but that is where that notation comes from. So looking at this notation, this diagram here where we've got Z, arg Z is the angle theta. Okay, so you can see here arg Z, the way that it's written, it's the shorthand for argument. It just means the angle that Z makes with the horizontal axis here. And as always, it's imagining that we're dealing with, a unit circle and that we're starting here. So it's the angle that is made with this point here with the horizontal axis going this way, so in the counterclockwise direction, as we normally do. So the way to figure this out is there's two things you could do. You could either, I'll just do this in purple, look at theta and think, okay, sine, which is opposite, remember that we've got opposite over adjacent, we've got sine of theta equals the opposite, which is b, over the modulus of z, which I'm going to call r, okay? Or you could also think about it dealing with cos, so thinking about the angle cos of theta would be the adjacent side, which is a over r. So that's two ways that you can think about finding theta. You can see here they've also expressed sine theta and cosine theta using the imaginary and the real notation. So imaginary z is b, and the real part of z is a, dealing with a complex number of this form. Okay, and here you've got just, instead of r, you've got mod z. So these are completely equivalent. Okay, the reason I put these here is this will be very useful to us later on when we look at the polar form. Now the way that I generally tend to work with the argument, these are good, provided you know what z is, what the modulus of z is. If you do, that's fine, you can use these to find the angle. The way that you would use these is to actually go with inverses. So inverse sine of b on r gives you theta, or inverse cosine of a on r equals theta, okay? The other way that I tend to do this, just because it is separate from using r, and if you do make a mistake with your modulus, you don't also affect your angle, is that I use tan, okay? So if we have a look here, you can see that also tan of theta equals the opposite, b, over the adjacent, a, or written with the imaginary and the real notation, tan of theta equals the imaginary part of z over the real part of z. So for me, whenever I'm trying to find arg z, I actually use this formula. So the arg z, which is theta, can be found by taking tan to this side. So taking the inverse tan, okay, of the imaginary part over the real part. Okay, so that's the formula that I actually use when I'm dealing with complex numbers and trying to find arg. I just like that because it doesn't actually use mod z. So if you do make a mistake with mod z or with finding r, your argument isn't going to be affected. So remember, the key thing to take away from this is the argument of z is the angle that that point z would make with the horizontal x-axis if you were to draw a line between the origin and that point z. Okay. Now the thing to notice here is that arg has a little a. This is often called little arg, which is a cute little name for it. Okay, little arg. As opposed to the next thing that we're going to look at, which is big arg. Okay, so this is called the argument of z, and do you see it's got a capital A this time? Now the key thing with, the key difference I should say, with the argument with the capital A and the little a, is that when you're dealing with the little arg, if you had, for example, a complex number, let's say here, I'm just going to do pi on 4 as an angle here to z. So we'll do z equals 1 plus I. That gives you pi on 4 as an angle. Okay. Then when you're looking at the arg here, you know that arg z equals the inverse tan, okay, of 1 over 1, because that's the imaginary part is 1, the real part is 1, so that would be the inverse tan of 1, which is pi on 4, which we know. We could find that, we can see that from the diagram. The thing about a little arg z is that it's actually the same if you go around 2 pi in either direction, or 4 pi, or any multiple of 2 pi. So if we were to go around, let's say, go around this way, plus 2 pi, then we'd have little arg of z equals pi on 4 plus 2 pi, which is 8 pi on 4, so 9 pi on 4. And that's actually still correct for this particular example because 9 pi on 4 sits here. Okay, so what that means is that we don't actually, we're not able to sort of say that our argument has to be within a set interval of values. It can be anything plus or minus 2 pi. So generally how that can be written for little arg, and I'll do this in red, is that little arg is your angle theta, and it's plus 2n pi for any n. So for n that is an integer, okay, integer multiple of 2 pi, so it can be 0 as well if it's just theta itself, and it can also be negative, so we're going to say that n is an element of z, positive and negative integers. Okay, so little arg is a little bit different because it doesn't have that any kind of limit on what that angle can be. Okay, now we're going to move to that big arg, okay, big arg of z. Now you can see that this actually has an interval, okay, over which the argument occurs, and that interval is very, very important, so you definitely need to write down what big arg is. The interval is between negative pi and pi, not including negative pi. So the way to think about it with a diagram, which I would draw, is that you've got pi, okay, you are allowed to go from this point all the way over to pi, and you can include that as an angle. So if you have a complex number that's sitting on this horizontal axis on this side, the angle would be pi. Okay, imagine that you've got sort of an asymptote just happening underneath here. So you can also look at the angle going this way, all the way around, not quite getting to negative pi. Okay, so you can count anything on this side as negative, so negative pi on 3, negative pi on 4, negative 3 pi on 5, whatever you want on this side, but you can't get up to this horizontal line here. So you're only allowed to cover this area and then also the horizontal, and then cover the angle from this side. Okay, so for example, something like this, if this was pi on 3, oops, the big arg for this, so the big arg for z, if this was my z, would be negative pi on 3. Okay, I have to give it in this interval between negative pi and pi. If I wanted to think about this as a little arg, I could actually give this as the little arg going all the way around. I'm allowed to do that. I can't cross over here with big arg, but I could for little arg. And instead of being 6 pi on 3 minus 1, so 5 pi on 3, this would be 5 pi on 3 here. Instead of being negative pi on 3, you'd have that. Okay, so they are different. There's just different ways of looking at the same angle. Just be very careful when you're dealing with complex numbers. Often they use big arg. Okay, and if you use the wrong type of argument here, you're going to lose your marks for that question. So be careful, because this does limit your interval. Okay, so we're going to look finally at polar form. This is the most important part where we're building up to here for expressing a complex number. So instead of expressing our complex number as a plus bi, we're going to do this a bit differently. So the proof of this is actually in your textbook if you want to have a look at it as well. But what I'll do is I'll show you. What we're going to do here is we're going to take this expression and we're going to do a little bit of algebra to it. What we're going to do is divide everything here by r. Okay, that actually changes the expression, so we're going to put an r out the front as well. What that means is you've effectively done nothing. All the r's would cancel and you're still here. Okay, now if we go back to our first slide, okay, you can see here that sine of theta equals b over r, the imaginary over the modulus of z, and cos of theta equals a over r. That's the real part over the imaginary, the real part over the modulus of z. So if we use those ideas, we can actually rewrite this now. So we have r out the front. A over r was cos theta, where theta was the angle that our complex number makes with the horizontal axis. And b over r is sine theta. And we still have the I there. And this particular form is what's known as polar form. Okay, so it has two things. And it's very important that you're familiar with this form. It has the angle theta and it has the modulus r. So they're the things that you're interested in. Okay. To find theta, remember that theta is equal to the inverse tan of the imaginary part of z over the real part of z. And to find r, that's the square root of the imaginary and real parts of z squared. So we'll use these formulas in the next few worked examples to find or to convert from our Cartesian form of a complex number to the polar form of the complex number. The reason that we do this, the polar form is very easy to work with when we're looking at powers and roots, and we're going to do a lot of that work in the following section. Well, one last really important thing I should tell you as well with the polar form is that this is often written in a shorthand way. Okay, it's called cis notation, and the reason it's called cis notation is for the C and the S, and typically with the complex number when it's written this way, what we tend to do is actually write, this I in front. Okay, so you don't have, it's really just so that it doesn't look like the angle is theta I. So this cis notation, or this word cis, comes from the fact that you have CIS in here, okay? And all it is just a quick way of writing this. Because the angle here is the same, you're effectively writing the same thing out twice. It's kind of a waste of time. So they write it in cis notation, cis form, as Z equals R, and they just use the abbreviation cis. C for cos, the I for the imaginary part, and the S for sine, and then the angle theta that you have there. So they're completely equivalent. You can use either one that you want. Okay, I often use this one because I quite like that one, but they're completely equivalent, and this is just a shorthand way. It's still polar form. It's often just referred to as cis form, and it's just the shorthand way of writing this, which is just got the actual cos and sine written in instead of here, which is short. So they're the forms that you're really going to need to understand: your Cartesian form and your polar form, either in the long way or in the cis form.